you. The next speaker is Vern Paulsen, who's going to tell us about algebras and synchronous games.
Okay, thank you. Really, two things I want to accomplish. First, I want to tell you a little bit more about these quantum correlations or quantum conditional probability densities. We've heard a little bit about them in Aram's talk. This is a set called Q, which we often try to look for solutions to games that are working. And then I want to tell you about a particular family of games which try to reduce deciding if they have perfect strategies or not to questions in algebra. And, these algebras, well, sums of squares show up, but trying to decide if one is in an ideal shows up, so it boils down to Grosvenor basis type algorithms. So that's the goal, is to try to maybe turn deciding if you have perfect strategies for games into questions that you can do purely with mechanical operations on these algebras. So the outline is, first I'll talk a little bit about these finite input-output games. Many of them I'm interested in are what are known as prover systems. Then I'll tell you about the quantum correlations and sort of the state-of-the-art of what we know about these and why we're so interested in them. And then I'll talk about this special family of games I want to focus on, these synchronous games, explain what I mean by synchronous. And then I'll show you how you associate an algebra to each of these games. And then I'll focus in particular on linear constraint system games and graph isomorphism games to show you what this algebra looks like and what we know about this algebra in these cases. So when I give this talk to math audiences, I spend a quarter of the talk explaining what on earth we mean by a game, because they'll say, and when you say the players are non-communicating, what does that mean mathematically? But you all know what it means. So I'm going to skip over that part, just draw the picture. So you have a referee, and you've got Alice and Bob. I draw a wall between them. That means they're not communicating. The only difference I noticed that Aram was using A's and B's for their inputs. And throughout this talk, I'm going to think of the inputs that they receive as X's and Y's. So you can imagine that the referee asks Alice question X and Bob question Y, and they return answers. So I've got the A's and B's and X and Y's that switched from your way of doing things.
Can you turn the blackboard light?
The last.
Well, I'll say I pick which one's A, B, and which one's X, Y randomly each time I give a talk. So.
Is that okay?
Yeah.
And then the game has rules, and you can think of the rules as a function from Alice's inputs, across Bob's inputs, across Alice's outputs, to 0, 1, where 1 means that they gave a correct answer, and 0 means they gave an incorrect answer. So the big thing is that Alice has to return her answer without knowing what question Bob was asked. But whether it's a good pair, a good returning pair, A and B, depends on both the inputs, the X and the Y input. So this equals 1 means they've done a good job, and if it's a 0, means they lose. So people often call this V for verification, and they sometimes call this a verifier instead of referee. But that's the idea behind the games. And now, if they're playing by some random strategy, this should produce some sort of conditional probability density. And so I like to write these this way. So this means this is the probability that they output the pair AB given that they receive inputs X, Y. So it's a conditional probability density. Okay, so here's all the stuff we're going to skip, trying to explain things. There's a cute little picture. Notice it's the X and the Y. And so They both know the rule function to start the game. They want to produce this good probabilistic strategy. And so this is all those things I said up until now. Strategy is perfect if the probability that it produces an incorrect answer pair is 0. So often I'm going to be looking at the case of whether or not we have a perfect strategy. So that's perfect in that way. And we're really interested in the case where this probability density either arises from classical shared randomness or by performing measurements on some shared entangled state. But the thing that's really interesting to mathematicians here is that there are multiple mathematical models for describing what the probability densities are that arise from shared quantum randomness. And so, so there's really several different sets we need to think about. So first off, I'll call C low the densities that can be achieved by classical shared randomness. This is because this is Einstein's locality hypothesis that goes on here. CQ will be the one that's almost everyone uses. You saw Aaron called this set capital Q the other day. It's where you assume that Alice and Bob each have their own state space, which is represented by some finite dimensional Hilbert space. And then the joint state space is represented by the tensor product of those two Hilbert spaces. And that's entangled, that's where the entangled states live. But there's also no reason that their individual state space should have to be finite dimensional. So some people study the case where you allow them to be infinite dimensional, and I'll use that by QS when I want to talk about that set. It turns out, well, for a long time we didn't know whether these sets were closed or not, but we did know that the closure of either of these two sets is the same, and so I'll call that set C sub QA, for these are the things, the densities that you can approximate by quantum densities. So that's what the A is for. And then there's this last model, which is very popular in sort of abstract quantum physics, which we call the commuting model, and I'll explain what that is in a couple of slides. So first off, you're in this first model. If and only if, well, there are these finite dimensional state spaces, one for Alice, one for Bob, saying that they have a shared lab we think of as this is the state space of the combined lab. So you have some unit vector in there, which could either be separable or entangled. And then the measurements, again, I'll slightly change. So for each input x, I've got a positive semi-definite matrix, one for each A. So for each pair, I've got these positive semi-definites, or projections if you prefer. And then saying it's a measurement system says that these, as you sum over all outputs, it has to add up to the identity. Ditto for Bob. And then the probability that if they perform measurement X and measurement Y, that they get outcome A and B is given by the inner product of that operator with the state vector. Now, many of you are used to seeing, I should have a density matrix here and be doing a trace, but there's a standard trick called purification that allows you to just enlarge the Hilbert spaces in a way that's still keeping them finite dimensional and replace density matrices by state vectors. And so, so there's nothing new gained if you put densities here. And then there's a second trick called the dilation trick that says if you have positive semi-definite matrices adding up to 1, then again you can enlarge the Hilbert space to slightly better and make them all into projections on that bigger space.
So the E's are positive semi-definite? Is it not? It says that. Okay.
Pardon?
The E's are positive semi-definite, the F's are positive semi-definite.
Yeah.
Okay.
Or projections. In fact, I'm always going to take them to be
So
projections.
you can just think of them as projections by the Nymark dilation.
Yeah, by the Nymark dilation. And so, so the point is, if you put traces against density matrices, or if you change these to be positive semi-definite instead of projections, set of all possible densities you can get is still the same set. So, we'll just use the most convenient way to write them. And then the CQS is just drop the hypothesis that these are finite dimensional Hilbert spaces. And you look at all the densities you could get that way. For CQC, and then CQA is that you take the closure of these sets. For CQC, we assume instead that there's a common Hilbert space. So this is the viewpoint that the universe is governed by some state space, and there should be, at any moment, there's some state. Alice has measurement operators acting on the universal state space, and Bob has them. And then the fact that their labs are separating and non-communicating is described by the fact that it doesn't matter which order they do their measurements in. So that's the commuting model. And then what a density looks like. So again, they still have to add up to the identity. Again, there's still projections or positive semi-definite, but it turns out you get the same sets either way. And then instead of a tensor product here, you have an actual product. So the way to sort of think of this is if you did EXA tensor 1, that would commute with one tensor FYB, and when you do the product of those two things, you get the tensor product. So there's the various different notions of what we could mean by quantum probability densities. And let me show you what we do know. So originally, Cyrilson claimed or conjectured, depending on which paper you read, that all of the model didn't matter, that you always got the same probability densities the same way. And it wasn't until 2017 that we proved that any of these were different. And the way Slostra demonstrated it was by using the theory of these games that we've been talking about over there. We found a game that had a perfect strategy in one set, but no perfect strategy in another set, and so the sets had to be different. So here's what we do know now, sort of bring you up to the state of the art. So if we assume that Alice and Bob both have n inputs and k outputs, and then I'll just put an nk to denote that. So these will be the PAB XYs. You can think of them as tuples living in an n squared k squared dimensional space. There's tuples. So the thing we've known forever, going back to Bell, is that the set of local densities and the set of quantum densities is different as soon as you have at least two inputs and outputs. The thing that got operator algebras and people in my community interested in these was around 2011 to 2013. First, Young et al. Connected this question about whether two of these sets were the same up with something called the Kahn's embedding problem. And then Ozawa showed the converse, that if you knew these sets were the same, that was actually equivalent to Kahn's embedding. So trying to separate these different notions of quantum things is this Kahn embedding problem. I'm not going to try to explain what it is. It's a problem that goes back to the mid-60s, and it follows from von Neumann was trying to do this classification of what we call von Neumann algebras. There were just 2 or 3 pieces he and Murray couldn't do in the 40s. Kahn did some of those in the 60s, and that's what he got his Fields Medal for. And then he also conjectured another piece of the classification question at that stage, and that's his embedding problem. Since then, it's been discovered to be equivalent to all kinds of problems in all kinds of different areas, which is one of the reasons it's kind of a linchpin problem in a lot of different areas. It's related to questions about whether all groups are hyperlinear or sophic, if you know some of these questions about groups. It's really questions in free probability. So it's one of, so for our field to advance, it has to be solved. And now we know it's also equivalent to some questions about what's going on in quantum physics, what about these various models. Okay. So, as I said, Slosser was the first one to show there was any difference. I guess I should have said, this one is known to be closed. This one is closed because you define it to be the closure. So he showed that CQ was not equal to its closure by showing it's not closed. His proof used a lot of implicit things. So there was an n, which is got to be roughly around 100 to satisfy all the equations. So for rather large n and 8 outputs, the set's not closed. We improved on that a little bit the same year. We showed that if you went all the way down to, so for small numbers of inputs and outputs, this set is not closed. And also, if you allow yourself infinite dimensions, that doesn't help. That's still not closed. Just last year, called D'Angelo and Stark, showed that you could separate these sets as long as, even in small dimensions, as long as you were 4 to 3. So basically, it's only for four inputs or 3 inputs that we don't know what's going on here, and that's still a lot of people trying to get these last few sets figured out. From the point of view of this workshop, the reason many people liked using this top set, and were hoping it was the same as the bottom one, was that this set is described as a decreasing sequence of spectrahedra by something called the NPA hierarchy. I think it was called the PNA hierarchy the other day. But it's a way to realize this as a decreasing spectrahedra. So it gives you good ways to try to find things in the largest set. You have fairly solvable problems there. Let me show you a little bit more about what we proved, because it's just stronger than saying the set is not closed. It says the set is really ugly. So what we showed is for all t in this interval, and you take your 5 inputs, then we can write down explicitly what a probability, conditional probability density looks like. So when the inputs are the same, here's the formula. When the inputs are different, here's the formula. And then we proved that this density is always in the closure, but to be in the set, it only happens when t is rational. So deciding membership in this set is at least as hard as deciding whether you've got a rational number or an irrational number. And so it shows this CQ set is, I forgot to say all of these sets are convex. So you've got this arc where the smaller sets, only the rational points on here are in the smaller set, but then the smaller set is convex, so also the line segments joining all those rational points is in there. It shows the set is pretty gnarly. It's not just that there's some little cusp point where it's not closed. It shows that the set CQ is sort of star-shaped or something with all these rational points on this curve out in the boundary. The other thing we did is for each value t, we created a game depending on t, so that this corresponding probability density is the unique optimal strategy. So many games without unique optimal, where the optimal is not attained. It really is a suit, not a max. Okay. Now let me explain what these synchronous games are. So synchronous games are games where Alice and Bob are being asked the same questions, and they have to produce the same answers. And anytime you have that, then it's perfectly reasonable that if they're asked the same question, they should give the same answer. So that's all a synchronous game is. Games where the inputs are the same, the outputs are the same, And if they get asked the same question, they have to give the same answer. Now, this means that each round of the game, they have to give the same answer. If they get asked the same question later, they don't have to give the answer they gave the first time. It's just, and that's the way they sort of disguise their solutions. So for density to be a perfect density for a synchronous game, it has to have this property that whenever A and B are not equal, then the probability is 0. And so we'll call such density synchronous, and then I'll just use a superscript S whenever I want to talk about a synchronous probability density. And remarkably, this one little, so let me first mention a few games. So one game that is synchronous is the graph coloring game. So the idea there is you've got a graph, and Alice and Bob want to convince the referee that they can see color the graph. So the inputs are vertices of the graph, and the outputs are colors. So the referee gives Alice and Bob a pair of vertices, and they return a pair of colors. If the vertices are adjacent, they have to return different colors, because that's the way graph colorings work. And the only other rule is that the referee gave them both the same vertex, they have to return the same color. Now, if you think about it for a second, if they only had to return different colors whenever things are adjacent, then Alice could always reply red and Bob could always reply green, and it would look like you were two-coloring every graph in the world. It's only the synchronous rule that prevents that. It's, when they get the same vertex, they have to return the same color.
So is this condition on the payoff, or it's a condition on the strategies that they have to do? Because for the coloring is somehow...
So what I'm doing is I'm describing the rules.
Right, no, but your assumption in here, like the synchronous assumption. Because for coloring, I mean...
It's a condition on the game, on the rules of the game. So
but optimal, so I want a condition on this such that the optimal strategies are
right, so if I have a perfect strategy for this game, then it has to satisfy this synchronous rule. Now, if I have something that's nearly synchronous, I mean nearly a perfect strategy, it only has to be nearly synchronous. And that's where things get touchy, is how to nearly synchronous behave compared to how synchronous behaves. Graph homomorphism games are another one. This is where you have two graphs. A homomorphism between a graph is just a function from vertices of the first graph to vertices of the second. So that if vertices were adjacent, then their images are adjacent. And so you make that into a game in a similar way. The inputs are vertices of the first graph, the outputs are vertices of the second graph. And whenever they're adjacent, they have to return adjacent vertices. And whenever they're both given the same vertex from G, they have to return the same vertex from H. The game that was described in the last talk is called the CHSH game, and that's not synchronous. There are games for solving systems of equations, and typically what they do is Alice is given an equation, and she returns, to win, she has to return a solution to her equation. And Bob is given a single variable, and he returns value from the variable. And then the winning pairs say that the value he returned for his variable has to be the same as the value Alice used for her solution. So that's the usual way these games are played. But they all have a synchronous version. And in the synchronous version, you give Alice and Bob each an equation, and they each have to return, to win, they have to each return a solution, and any variables that were in the first equation, variables in Alice's equation and variables in Bob's equation, have to be assigned the same value. So that's the way the rules of those games go. And it turns out for these systems, one has a perfect strategy if and only if the other does. And then the most recent game that's been studied a lot is the graph isomorphism games. So two graphs are isomorphic if you have some one-to-one function from vertices of one to vertices of the other, so that it preserves all the adjacency relations. And you make that into a game in a similar fashion. that game has an extra property that I won't really talk about in here, but it's what's known as a bisynchronous game, because in synchronous, if they're given the same, asked the same question, they have to return the same answer. Bisynchronous says also if they're asked different questions, they have to return different answers. So it's a one-to-oneness condition on a synchronous game. So that's a few examples. And now, why are synchronous correlations suddenly more magical? Well, in this paper with Severini, Stalpi, Tagora, and Winter, we were first studying the graph as coloring game, and we wondered what was so special about it. We discovered that it's synchronous. And if you have a density that obeys this synchronous condition, then it turns out you can ignore Bob. But if you just look at the, say you look at Alice's projections and you looked at the algebra they generated, then there would have to be the trace, then the original state would have to be a trace. So there's always a trace, so that when you do products of Alice's things and take the trace, that gives you the probability density. So for those of you who are not familiar with a trace on an algebra, it means it's a functional that sends 1 to 1. So if you think of the trace on matrices, we're just normalizing it. But then also the other property of the trace on matrices, if you do x times y, the trace of xy is the same as the trace of yx. So if you have an abstract algebra and you have a functional that has that property, sends 1 to 1, and sends positives to positive numbers, then that's what's meant by a trace on the algebra. And so it turns out if you just have a trace, then it turns out you can build Bob's operators from just knowing this trace. And if you want to know if it's a trace that lives in this original set Q, that's if and only if the algebra up here can be taken to be finite dimensional. What all finite dimensional C-star algebras are, they're direct sums of matrices. But then the way the trace can behave is on each block, it's the trace, but then with some weights so that the weighted traces add up to 1. So that's so there aren't that many traces in finite dimensions. At the time, we couldn't figure out how to characterize the traces that were in the CQA, and that was what was done a little bit later. So the first big surprise is if you do this infinite dimensional tensor product and you just put this synchronous condition on, then you can't possibly have any more, you don't generate any new probability densities. So if you have a game, a synchronous game that has a perfect strategy using infinite dimensional and tensor product, then you could have done it with finite dimensional. And then we finally characterized what being in here is, and that's if and only if there are projections in. There's this very special algebra that shows up in Kahn's embedding conjecture, and it's if and only if you can find projections in that special algebra so that you have a trace. So this sort of links back, it sort of shows the first link back to this Kahn stuff, and that his special algebra is what shows up here. So just to remind you, if you don't demand that the density is a synchronous density, then Coladangelo and Stark showed these two sets are different. But if you look at the synchronous things in here, they're always the same. So just this one little linear constraint on the densities drops you down to the smaller thing. And then we're able to show sort of analog with the Yonga-Ozawa things, that if you want to study Kahn embedding, it's enough to study this smaller family of synchronous probability densities. Okay, so back to games. So if I have a synchronous game, it's got inputs I and outputs O, and it's got its rule lambda. By the star algebra, I just want to look at a universal algebra. So these are algebras in non-commuting variables. We heard a lot about polynomials in non-commuting variables, and that's all these are. But the number of variables I have is, I've got one variable for each input and one variable for each output. And now, the reason I have a star is to describe something being a projection, I need it to be equal to its adjoint, and I need it to be squared. So that's where why there's the star on these. So the first relation is that they should be algebras of projections. The second relation is, it's exactly this thing we need for it to be a measurement system, that they should sum up to 1. And then all the other relations come from the synchronous conditions. So if they have the same input, they're not allowed to give the same output, so I'll just describe that by saying that pair has to be 0. And then anytime I have a rule that's broken, then that product of those elements has to be 0. So really what you mean by a free algebra with generators and relations is you're going to take just polynomials in these, and then you gather all the relations and you look at the two-sided ideal generated by the relations, and you're going to quotient out by it. So these are really like cosets or images in the quotient, but I'll still give them the same letters, because otherwise it gets too annoying. Another way to think of this is these.
One question. Can I ask you, why doesn't the third condition follow from the second one?
It does. You'll see why I wanted to group these first three together, though.
Oh, okay.
It's because if you look at the first three, that exactly describes the group algebra of the, you take the free product of n copies of the cyclic group of order k. So cyclic group of order k, what it looks like is for each input you've got an element, a unitary, whose k power is 1. That unitary has spectral projections, that's the EXAs. So inside this group algebra, it's exactly described as the universal algebra with those relations. So you can also think of A as the group algebra, modulo the ideal generated by just these relations, which is why I grouped them in this particular way. But you're right, the third is implied by the fourth, but I wanted a grouping. So that's the other way to think of this algebra. Well, why do we care about this algebra? Well, it turns out everything you want to know about perfect strategies is contained in the algebra. So having a perfect classical strategy, that's the same as saying you have a deterministic strategy, and that's if and only if and only if this algebra has a non-trivial one-dimensional representation. But it's also the same as if instead of thinking of non-commuting variables, you thought of commuting variables, and you formed the ideal. It's saying that one's not in that ideal. So that means you've got a Grosvenor basis algorithm for deciding if you have a perfect, it turns deciding if you have perfect classical strategies exactly into a Grosvenor basis problem. Because you've got to decide if one is in a certain ideal, and you can do that with Grosvenor basis algorithms. Having a perfect quantum strategy in the finite dimensional thing is the same as saying this algebra can be represented by finite dimensional matrices. So you can find projections on a finite dimensional space satisfying all the appropriate relations. Having a perfect quantum commuting strategy is exactly the same as being able to embed this algebra inside a C-star algebra that has a trace. And having a perfect QA strategy is exactly the same as being able to embed this algebra into this special algebra that shows up in the Kahn conjecture. So what we were hoping to do is turn these, see if we can turn these last three things into algebraic properties, or at least this one, because we know we've got this for the QC. We know the QC strategies are described by these spectrahedra, so we should maybe be able to make things behave well. So the first one we looked at was this graph coloring game, which there's the fancy name it goes by. So when I want to talk about its algebra, I'll talk about algebra, that game. And, oh yeah, so I already discussed this a bit. But let's just say what we know. So it's known that this game has a perfect local strategy, if and only if you can actually k-color the graph. But it's known that there are lots of graphs for which you can have perfect strategies with far fewer number of colors than the best coloring, in fact, exponentially smaller. There's a family of graphs called the Hadamard graphs, for which, well, the coloring numbers aren't known exactly, but there's lower bound on them that's exponential in n. But there's a perfect strategy for coloring this with just quantum strategy for just n colors. So if you think of sort of a quantum chromatic number, these graphs all have quantum chromatic number n. So quantum chromatic would be the smallest number of colors for which you have a perfect strategy for the graph coloring game. It's quantum. And this shows that that quantum chromatic number can be exponentially smaller than the actual coloring. For graphs, we don't know if we can separate the best strategies for, say, QC coloring the graph from Q coloring. We don't know if there's any difference or if they're all the same. But so we thought, well, maybe this QC we can characterize by studying the algebra. What if you just know that the algebra is non-zero? So let's look at what this algebra is. So it has generators, one for each edge of the graph. That's the inputs, and one for each color. It always has those first three relations. And then the last relation is that whenever two edges are adjacent, their colors can't be the same. So the product of those elements has to be zero. And then in this paper with Bill Helton, Meyer, and Matt Satriano, we were able to use a Grosvenor basis algorithm, a non-commutative one, to show that for any graph, as long as you have at least four colors, the one is not in the ideal. So that means that the algebra is non-zero. So in a certain sense, if you just ask for this algebra to be non-zero, it doesn't give you much information. In that sense, every graph would be four-colorable. The algebra is non-zero for every graph. So how about systems of equation games? So here, they want to convince the referee they've solved the systems of equations. Inputs are an equation, outputs are variables for the variable. They win if they return values that satisfy their individual equations, and for any variables they have in common, they return the same values. And again, this game has a perfect local strategy if and only if the system of equations has a simultaneous solution. So in that sense, the game is a prover system. If you can play it perfectly, probabilistically, then you actually solve the system. But there are many systems of equations with no simultaneous solution to perfect quantum. The most famous one was, Merman was the first one to study these, and his so-called magic square is one. The idea of the magic square is you have 9 variables. And you think of putting them as the entries of a 3x3 grid, and you demand that these 3 variables add up to 1, these add up to 1, these add up to 1, that all the column variables for each column add up to 0. And you obviously can't solve that system of linear equation with, this is over the binary field. But it turns out there's a perfect quantum strategy that convinces the referee you really have solved it. So, and then Slofstra's was based on this same idea, but he had a system of roughly 100 linear binary equations for which he could show there was no perfect strategy that was quantum, but there was a perfect strategy in the closure of the quantum densities. And that's the way he showed the CQ and the CQA were different sets. But writing down 100 equations in roughly 100 unknowns is pretty tricky. So if we do this synchronous version instead, where they're both given inputs as, both given equations as their inputs and both return solutions, if say you had a linear system CX equals D, and here's what the game looks like. So for each equation, for each I, you've got an output which will be a vector in Z2 to the n. And then that vector should be a solution to the ith equation. So that ends up meaning that this element you can prove in the algebra it's always 0 if it's not a solution. And then the rule on products is that in EIA and in EJB, that product is 0 if A and B are inconsistent solutions, meaning there's some variable that they both had to involve where they took different values. And so it's the algebra generated, so fairly complicated algebra, lots of inputs, m inputs, 2 to the n outputs, and those rules. But what we proved in this most recent paper is that this game has a perfect QC strategy if and only if 1 is not just in the ideal, but something that we call the hereditary closure of the ideal. And here's where the sum of squares comes in. So if you're given an ideal in an algebra, suppose you have a summation of polynomials which lands in the ideal. Well, it turns out that that does not imply that each individual polynomial is in the ideal. So an ideal is called hereditary if it has the property that whenever a sum of squares lies in the ideal, then each element was in the ideal. So if you have it, so ideals aren't in general hereditary. But you can always take a smallest hereditary ideal containing your things. But the way it's defined is not algorithmic. It's only an existential proof. And so we don't really know very well how to deal with this hereditary because we don't really have a constructive way to build the hereditary closure of an ideal yet. And that's where the sum of squares question really comes in. Is there a way to figure out how to make an ideal hereditary that's algorithmic instead of existential? Because if there was, then you could reduce this down to a machine problem, and that would tell you exactly when you have perfect QC solutions.
I might comment, I mean, it does boil down to a semi-definite program. The trouble is that it's just too big a semi-definite program. So it's a question of size of the...
Well, also, the other problem is, you see, if you start with this, then you want to add these PIs. But now you have a larger ideal because you've thrown in the PIs. And now that larger ideal might not be hereditary. And so
you just do it again.
You do it again, and you do it again, and you do it again. Does it terminate? I don't know. So that's why it's only defined existentially, not algorithmically, because we don't know if the process of each time you have PIs, adding them to the ideal and then looking at this bigger ideal and then repeating, if that comes up from below, if that ever terminates and hits the hereditary closure of the ideal, or if there's more you got to do. But if we could solve that problem, then this would give a purely algebraic way of deciding if you have those perfect strategies. And now, just a couple of words on this graph isomorphism game, because that's the one where everything does seem to work best. So we'll just use ISO-GH to denote that game. So the inputs are the vertices of G, the outputs are the vertices of H. And here's kind of the easiest way to describe the rules. If we define a relation by, if things are edges, we'll assign -1 to the pair. If they're equal, we'll assign 0 to the pair. And if they're not an edge, we'll assign 1 to the pair. Then the rules are simply that if they receive G1 and G2, and they return a pair of vertices from the second graph, then they win if and only if the relation between the first set is the same as the relation between the second set. So if the relation was that the first pair are equal, then the second pair has to be equal. The relation was that the first pair were adjacent, then the second pair has to be adjacent. And if they weren't adjacent, they also have to stay non-adjacent. So there's the rules of the game. And now you want to ask, does this have a perfect quantum strategy, perfect QC strategy, and so on? Again, you can prove it has a perfect probabilistic strategy, the Loc strategy, if and only if the graphs actually were isomorphic. So in a sense, this game really does capture graph isomorphism. There are many graphs that are not isomorphic and have perfect quantum strategies. And it's also known that there are pairs of graphs that are QA isomorphic, but not Q isomorphic. So this game also separates the Q and the QA sets. Here's what the algebra looks like. It's going to have generators, E sub GH, one for each G, one for each H. Of course, you've got to add up to 1. But the other surprising thing is if you freeze an H and sum on the G's, that also has to add up to 1. And this is known as something called a quantum permutation. Whenever you have a set of projections which add to 1 along the row and 1 along the column, we think that is a quantum permutation. Here's the reason for that. If you think of what a permutation matrix is, each entry is 0 or 1. How do you quantize that? You say, well, each entry is a projection. And to be a permutation, it has to add up to 1s along rows and 1s along columns. And so the way we quantize the idea of a permutation matrix is we replace the value is 0 or 1 by the value as a projection. And then the other rules can be summarized this way, which is an ugly-looking formula, but it's actually nicest if you write it as a matrix. So if you take this matrix of projections and you multiply it on the left by the adjacency matrix of G, it makes sense to multiply things by scalar matrices. And you multiply on the right by the adjacency matrix of H, it has to intertwine them. So it's exactly the algebra with these generators and this, these two things, this summing to 1 along rows and columns and intertwining, that's exactly characterized as the properties of the algebra. That gives all the generators and relations. And then what we were able to prove is that this algebra, this game, is nice enough that having a perfect strategy is exactly the same as showing that this algebra is non-trivial. So i.e. exactly the same as proving that 1 is not in the ideal generated by relations. So for these games, you can try to run a Grosvenor basis program. If it gives you a Grosvenor basis that doesn't contain 1, then you know 1's not in the ideal, and you know the game that you could build a perfect QC strategy for the game. So without having to come up with the densities, the operators, or anything, you just study the algebra. So here's a case where everything works perfectly in our sense. The game, the algebra, you can really reduce perfect strategies down to just a property of the algebra. Very recently, there's been some great progress. Nanciska and Roberson just within the last 2 weeks, posted a paper where they proved that this graph isomorphism game has a perfect strategy if and only if, for every planar graph K, you count the number of homomorphisms from K to G, and that has to be the same as the number of homomorphisms from K to H. If that's true for all planar graphs, that's exactly the same as having a perfect QC strategy. So our hope was that maybe we can prove this by using our theorem. And what it boils down to is their result is the same as proving that 1 is in the ideal if and only if you can find a planar graph where these are different. So, so in one direction, you'd like to use this planar graph to somehow build a way to write 1 is in the ideal. And then conversely, you'd like to show if you can't, then there can't be a planar graph. This result of Van Siska and Roberson is very surprising, but well, first off, it's very deep and it's very hard. But it also if you've seen Lováš's theorem, you'll understand the motivation a little bit. So Lováš proved that 2 graphs are classically isomorphic if and only if the number of homomorphisms from K to G is the same as the homomorphisms from K to H for all graphs K. So what they showed is that QC is a relaxation of that, and it just relaxes it to replacing all K by planar K, which is really remarkable. But again, you could try to give a new proof of Lováš's theta by using our algebra. What it boils down to is if you just took the abelian version of our algebra, then Lováš's theorem is equivalent to this statement, that 1's in the ideal if and only if this. We still don't know what happens for Q or QA isomorphisms, but there should be something between all graphs and planar graphs that characterize the Q and the QA isomorphism graphs. Well, I say I've ran over a bit, so we'll stop there. Thank you.
Questions?
Also, no questions. I think that.
I asked a question.
Oh,
It's a while back.
yeah, but you don't count. Aaron, he counts.
So this is kind of very general, but what are the? I mean, these facts where you can figure out if there's a perfect strategy based on whether the algebra contains, whether it's 0 or not. Like, what are the? Can you say something about like the specific features of the games that let you do this? Like, what is it? What is it about isomorphism?
Yeah,
Homomorphism
so
game.
the graph isomorphism game has this property that I call bisynchronous.
Okay.
Because the function is supposed to be 1-to-1, if you look at the rules of the game, anytime they get different vertices, they have to return different vertices. And so it's synchronous and has that property. And so we've been studying games that are bisynchronous, and our hope is to prove the analog of this theorem for any bisynchronous game. That deciding if it has a perfect QC strategy will be exactly the same as deciding whether 1's in the ideal of the algebraic relations or not.
So graph isomorphism is really kind of a pretty general game in that sense.
Yeah. And the way these other things go is like this linear systems games embed inside graph isomorphism games. But the way the embedding goes, it's one way, and that's why we run into this hereditary ideal problem.
Okay.
But so there's many. We don't know exactly which games can be converted to graph isomorphism games, and that's one of the things here. We think that maybe every bisynchronous game can be converted to a graph isomorphism game somehow. Not just embed inside, but there's a way to build a graph out of the game rules. So the game really is a graph isomorphism.
Okay.
Yeah. So this Robertson theorem, like I guess one implication is that to prove that this game does not have a perfect QC strategy, it tries to exhibit this graph, planar graph.
Yeah.
So was it known that you could prove that efficiently before? I mean, K is
Well,
restricted size. Right?
Nothing is known about how efficient this is. Like I said, they posted this 2 weeks ago. So.
But what I mean is the size of K, like, is there an upper bound on the number of vertices of K, for example?
There's nothing like that in their,
okay.
in their proof. It's purely existential. So, they start with a planar graph for which these are different, and they start doing things, and then they prove if they have. But what's interesting is their proof goes, if they have one of these quantum permutations that intertwines like this, then they're able to fairly efficiently prove that necessarily just this condition implies that for all planar graphs, the cardinalities of the homomorphisms have to be the same. So the one implication is quite easy. But it's a bit tricky to see why it only applies for planar graphs. Because it doesn't apply, knowing this doesn't imply the cardinality is the same for all graphs, only for planar. But that's well, so one half of their proof is easier than the other half. This goes most often with proof stuff.
So all these computations, if I understand correctly, they're non-commutative Gardner basis calculations.
Yeah.
So are there somehow decidable? I mean, in this particular case, or are there subclasses for which?
No, it's exactly the same. It's a halting problem. If it stops.
Right, but you have more
basis.
structure, right? I mean, you have more structure in there.
Yeah.
Does some of these generalize to more players?
Yeah, you can play games with 3 or 4 or 5 players. Synchronous games turn out not to be so interesting when you go to multiple players. So I can prove that as soon as you take something that's synchronous and it has 3 players, then it has a perfect quantum strategy, if and only if it has a perfect local strategy. So amazingly, that synchronous condition really wipes out everything as soon as you get a multiplayer. It's only interesting for 2-player games, which is why I've really focused on the on-2-player games.
Was that used by? Was that observed by like Vide or Kempe or something like that? Or am I getting mixed up?
About the multiple,
yeah,
the synchronous going away
for 3 players.
3 or more. Well, I don't know. I observed it, and I've told lots of people about it. So maybe somebody remarked on it someplace. It's basically if you have something that's a trace, and if you have 3 players, then not only can you reverse x and y, but if you have an x, y, and z. No matter which order you write them down in, the value of the functional is the same. And then you can use this to prove that the functional is actually a homomorphism. So as soon as traces take care of all permutations of 3 things, then they have to be homomorphisms. And that's so then you have a homomorphism into the complex numbers, and so then you have a perfect classical strategy. That's the proof.
Sorry, just checking. When you say synchronous for 3 players, is the condition that you ask 2 players the same thing, the 3rd player anything, those 2 players agree, or is it you ask all 3 players the same thing?
If you ask all 3 the same,
They all agree.
then they all 3 have to agree. Cool. But if only 2 of them are asking, you don't make. So it's the sort of the most stringent version of synchronous already buys you that it's has to be a community. And it's just this little game with traces. And it uses Cauchy-Schwarz, which Barack would like.
Okay, if there are no other questions, then let's start again.